Following up on the definition of a monomial function, we are now ready to define the nth root of a real number. To do so, we will use the inverse function of a monomial of degree n, and we will have to be careful to consider the cases when n is even and n is odd. In order to master the content of this lecture, you will need a good understanding of the relations between a function and its inverse, and you will also need to recall the results about graph transformation. Let's start by recalling the two families of monomial function that we went over in the last lesson. So we saw that there were two families of graph y equals x to the n. One family for n odd, for example, here we have y equals x to the first power, and then the second one is y equals x cubed, and the third one is y equals x5. You remember that the graphs are getting straighter and straighter, steeper and steeper as the exponent increase. These are not U-shaped graph. And then we had the second family for n even. For example, here it's y equals x squared, the parabola that we studied before. Then we have y equals x to the fourth, and then y equals x to the sixth. Again, we see that the graph gets straighter and straighter, or narrower and narrower as the power increases. Okay, so now we can ask ourselves which of these functions have an inverse. If we look at the first family for n odd, we see that any of these graphs will pass the horizontal line test. Therefore, all of these functions are one-to-one. Therefore, they all have an inverse function. So I can say that for n odd, f of x equals xn is one-to-one, so it has an inverse function. There is a function f inverse of x. Question is, what is f inverse of x? We will answer it very soon. Now, on the other hand, when we look at the families of function y equals xn for n even, none of these graphs will pass the horizontal line test. Therefore, none of these functions are one-to-one. They do not have an inverse. Therefore, we can ask ourselves, is there anything we can do so that the graphs are one-to-one, the graphs will pass the horizontal line test? And the answer is yes, there is. And it's a very easy way to rectify the situation. We're going to eliminate the part of the graph that makes a function fail HLT. What am I saying here? Well, that's very simple. I'm just going to eliminate this portion of the graph. And now you see with the left side eliminated that all the right side will pass HLT. Every graph will have an inverse graph. Every function has an inverse function. Of course, I'm not looking at what's going on right here because I have eliminated that. It doesn't count. Now, how do we eliminate a portion of a graph? Well, that's simple. Instead of defining the function y equals x to the n over the domain negative infinity, infinity, I'm just going to define it right here. I'm not going to look at this side. So my new domain is going to be 0, infinity. And for x's in 0, infinity, then the function x to the n is one-to-one. Therefore, there is an inverse function. Okay, and the question is, what is the inverse function? That's what we're about to define now. Before we define the inverse function of a monomial, though, one more remark. You can see that the range of all of these functions for n even is the non-negative set of real number. The range is 0, infinity. So right here we have range is 0, infinity. While for an odd monomial, you can see that the range is the entire set of real number. So right here, the range is negative infinity, infinity, just like the domain. These are all defined over negative infinity, infinity, and they're all one-to-one for n odd. So now let's look at two statements. Here's the first statement. In this statement, I'm just recapitulating what I just went over. For any odd value of n, the monomial function f of x equals x to the n, whose domain is negative infinity, infinity, and range is negative infinity, infinity, has an inverse function. Remember, the entire graph passes HLT. On the other hand, when n is even, then the monomial function f of x equals x to the n will be one-to-one, will have an inverse only when I restrict the domain to 0, infinity. And the range of this function is going to be 0, infinity. All right, so now let's define the inverse function of these two families. Here are the defining statements for an nth root of a real number. It is the inverse function of a polynomial of degree n. We just need to be careful. If n is odd, a polynomial of degree n has an inverse function from its entire domain to its entire range. So the nth root is defined over the set of real number. That is, when n is odd. On the other hand, when n is even, a polynomial of degree n has an inverse only when I restrict the domain of the function to 0, infinity, including 0. The range of that function is also 0, infinity. So the nth root of a real number, when n is even, is only defined for non-negative value of x. This is a little bit theoretical. In application, it is very simple. Let's go over a few examples. In example number 1, we are asked to find the fourth root of 16. Before I do so, let me quickly recall the relation between a function and its inverse. So, if a function f has an inverse, and if I have f of a equal to b, then this statement is equivalent to a equals f inverse of b. Okay, now this fourth root is an inverse function right here. So basically, I'm on this side of the equation, and I have the fourth root of 16. Now, suppose this is a, then this statement is equivalent to, well, what is the function? The function is the exponential of degree 4, monomial of degree 4. A to the fourth equals 16. Now, do you know of a number a so that when it's raised to the fourth is equal to 16? Yes, we do. And that is 2. Why? Because 2 to the 4 is 16, so a is 2, and that is what I wanted to find, a, right? So the fourth root of 16 is 2 because 2 to the fourth equals 16. All right, second example then. What is the cube root of negative 27? So again, assume that the cube root of negative 27 is equal to a. This statement is equivalent to a cubed equals negative 27. So what number raised to the power of 3 is going to be equal to negative 27? Well, we know that 3 cubed is 27. 3 times 3 times 3 is 27, right? But that's not negative 27. But we also know that if we raise a negative number to a cube, we're going to find a negative answer. And so negative 3 cubed is negative 27. Therefore, the cube root of negative 27 is negative 3. I hope you start understanding how simple these problems are. Let's move on. Example number 4. What is the fifth root of 32? So again, assume the fifth root of 32 is a. Then this statement is equivalent to 32 equals a to the fifth. What number raised to the power of 5 is 32? Well, you can use a calculator here, but I do expect you to know that actually. And it's 2. 2 times 2 times 2 times 2 is equal to 32, right? So a is 2. So the fifth root of 32 is 2. All right, the next one is example number 4. I have to find the fourth root of negative 81. Well, that's going to be a tricky one, right? Check it out. So suppose the fourth root of negative 81 is equal to a, This statement is equivalent to negative 81 equals a to the fourth. Wait a minute. A number raised to the power of 4 equals a negative number? That is not possible in the set of real number, right? So a cannot be a real number. So because this year we're only working with real number, this is not defined in R. This is not a real number. If you want, you can say not a real number. Okay, so this is not a real number. And this is what we said in the statement. Check out the statement. We said when this n is even, then the input of the root must be positive. This is not defined for a negative input. Okay, all right, let's move on to example number 5. So in example number 5, I'm supposed to find the ninth root of negative 1. So suppose the ninth root of negative 1 is equal to a. This statement is equivalent to negative 1 equals a to the ninth. Now, do you know of a real number so that when you raise it to the power of 9, you find negative 1? Well, that's easy, right? That's going to be negative 1 because negative 1 to the ninth power, right? Negative 1 times negative 1 times 9 times is going to give you negative 1, okay? So this number is negative 1, all right? Next one, number 6. What is the cube root of 125? So if this is a, then this is the same as 125 equals a cubed. Do I know a number a so that when I cube it, I find 125? Yes, I do. That is 5. So the cube root of 125 equals 5 because 5 cubed is 125. Okay? All right. I'm going to let you work on number 7. How about number 8? What is the eighth root of 0? So if this is equal to a, that means 0 equals a to the eighth. What number raised to the power of 8 give you 0? Well, better be 0, right? If you take any other number, it's not going to give you 0. So this is simply 0. I'm going to let you do number 9. Let's do number 10 together. What is the cube root of negative 8? The cube root of negative 8 is equal to a if and only if negative 8 is equal to a cubed. Now, do you know a number so that when you cube it, you find negative 8? You should, and this number is negative 2. Negative 2 times negative 2 times negative 2 is negative 8, right? So a is negative 2. Okay, let's go over the second set of examples. Before we do so, though, let's quickly go over this obvious statement. It's a property. What happens when you take the nth root of a number and you raise it to the power of n? Well, again, let me remind you. If the nth root of x is equal to a, this statement is the same as saying that a to the n equals x, right? So look, right here. If you raise this to the power of n, what are you going to find? Where you're going to find a to the n is x, you're going to find x right here. Okay, so the nth root of a real number x raised to the power of n is always equal to x whenever this expression is defined. Okay, so now let's go over some more examples. All right, what is the cube root of 27 squared? Well, the first thing I'm going to do is find the cube root of 27. What number cubed give you 27? That's 3. 3 cubed is 27. So the cube root of 27 is 3, and 3 squared is 9. Pretty simple, right? Next one. Well, this one is the seventh root of negative 23. Do I know the seventh root of negative 23? I don't know it. It is a number, but I don't know it. I would need my calculator for that. But actually, I don't care because I'm taking the seventh root of negative 23 and I raise it to the power of 7. So I'm going to follow the property that is telling me that the nth root of x raised to the power of n, right? If it is the same thing right here, this is just x. So I don't know what the nth root of negative 23 is, but the result of this operation is negative 23. That's it. All right, 14 and 15. All right, so what am I raising to the power of 5? The fourth root of 16. Do you know a number so that when you raise it to the power of 4, you find 16? You should. That is 2. The fourth root of 16 is equal to 2 because 2 to the fourth is 16. And 2 to the 5 is 2 times 2 times 2 times 2 times 2 is 32 Make sure you do know this, please, okay? All right. Cube root of negative 8. What is the cube root of negative 8? The cube root of negative 8 is negative 2 because negative 2 cubed is equal to negative 8. So this is negative 2 to the power of 4. So negative 2 times negative 2 times negative 2 times negative 2 is 16. All right. I'm going to let you do number 16 and 17 on your own. Let's move on. 18. Ooh, this is kind of weird. The 11th root of negative 1 to the 26th. Well, let's first figure out what's the 11th root of a negative 1, right? So this is a number so that when you raise it to the power of 11, you find negative 1. Well, it shouldn't take long to figure out that the number better be negative 1, right? Negative 1 to 11 is negative 1. Negative 1 times negative 1 times negative 1, 11 times is negative 1. So right here, I take negative 1 and I want to raise it to the power of 26. So now I'm raising negative 1 to an even power. That is going to be plus 1. Okay, that's it. It's that simple. Number 19. Oh, this is not a value that I'm going to find. It's an expression, right? So, okay, this is a fifth root of an expression. So basically, I don't care what I put inside. The fifth root is always defined. So I don't need to assume the fifth root is well defined. It is always well defined. But what am I going to do to it? I'm raising it to the power of 5, right? So again, we are following this property. If you take the nth root of a and you raise it to the power of n, you're going to find a. So this is just negative 2x squared plus 3x minus 5. The index right here is the same as the power right here. This is called the index of the root, okay? All right, in example number 20, we're looking at the 6th root of an expression again, and we want to raise that to the power of 6. This is a little bit more delicate, right? Because it is a 6th root, and you know that what you have inside a 6th root has to be positive. So we should make sure that x to the 4th plus x squared plus 1 is always non-negative. But if you look at all the terms that you're adding, here's a power of 4, here's a square, and then you're adding 1, there's no problem. This is always going to be defined. So this is an expression that is actually always defined. So I'm going to use the same formula that I used before. The nth root of y to the n is equal to y. So this is just x to the 4th plus x squared plus 1. That's it. Okay, let's finish by looking at the graphs of an nth root. Now, to understand the graph of an nth root, I just want to go over two specific examples. I'm going to be looking at the cube root graph and the 4th root graph. To understand a general nth root graph, it's going to be very similar to the cube root or the 4th root, depending if n is odd or even. So let's see what the cube root of x looks like. So for that, I took the function y equals x cubed, and I want to graph its inverse function. So you know how it works. You have to take the symmetrical of y equals x cubed through the line y equals x, right? So first, let's grab the points that are on the mirror, right here, 0, 0, 1, 1, and negative 1, negative 1. And then the next point on the graph of y equals x cubed would be 2, 8, right? So 2, 8 is right here, right? So 2, 8 becomes what? It becomes 8, 2. So 5, 6, 7, 8, 2 right here. And of course, I also have negative 2, negative 8, which becomes, so this is, here, let me write it down. This is negative 2, negative 8, and that becomes negative 8, negative 2. So negative 8, 6, 7, 8. Negative 8, negative 2 right here, okay? So that's it. I have this point, this one, this one, this one, and this one. I can graph my cube root function. It's going to look like this. So this is y equals cube root of x right here, okay? So this does look like an elongated S, right? An elongated S. And in general, any y equals nth root when n is odd will look like an elongated S. You see what happened when you increase the power of the root, the graphs are becoming steeper. We went over that, right? And so what's going to happen for the nth root, when you increase the index of the root, the graph are going to get closer and closer to the x-axis, flatter and flatter if you want. I'm not sure that's the right term. Okay, let's look now at the 4th root graph, okay? So on this graph right here, which is y equals x to the fourth, I want to graph the fourth root. So I'm looking at the inverse function of the fourth root, and that's x to the fourth. Of course, defined for x positive, right? We have the point 0, 0, 1, 1, 1 to the fourth is 1, and then 2 to the fourth is 16 right here. That's 2, 16, okay? So let's grab the points on the inverse graph. So I'm still going to have 0, 0, and 1, 1. It's a point on the mirror. And then 216 will become 16, 2. Now, I don't have enough right here number. I should have written up to 16. So right here, 2, I got a graph 16. So you see, basically, you're dealing with a graph that is very, very, very flat again. And there's a point right here that is 16, 2, okay? And all the nth root will be flat like that. If you look at my notes, I wrote a couple of nth root for n odd and n even. Let's do one more example about graph shifting either the cube root or right here, the fourth root of x. Okay, last example. So in this example, I'm going to do a couple of graph transformation. What do I start with? I start with the fourth root. I just went over this graph. I'm only going to get 3 points on it, okay? We'll see which one. And then I'll do y equals the fourth root of x plus 5. That's 5 units to the left. Next one will be y equals 3 times the fourth root of x plus 5. So I'm going to multiply all my y's by 3. And finally, the last one will be y equals 3 times the fourth root of x plus 5 minus 4 down. All right. So let's start with the original one, the fourth root of x. So I know what I want. The fourth root of 0 is 0. The fourth root of 1 is 1. 1 to the fourth is 1. And then which fourth root do I know here? I don't know the fourth root of 9. I don't know the fourth root of 12. I know the fourth root of 16. Again, this is something we just went over. What number raised to the power of 4 is 16? That's 2. Okay, because 2 to the fourth is equal to 16. So the fourth root of 16 is 2 right here. And I have that's the fourth root of 16. Y equals fourth root of fourth root of x. So next, what do I want to do? I'm going 5 to the left. So this point goes right here. This point goes right here. And this point, 1, 2, 3, 4, 5 goes right here. Here's in green. This is the fourth root of x plus 5. Next one, what do? I multiply all my y's by 3. So 0 times 3 is 0. 1 times 3 is 3. And 2 times 3 is 6 right here. This graph is y equals 3 times the fourth root of x plus 5. And finally, I want to go down 4. So 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4 right here. So this is my final graph. Here we go. All right. I hope it was clear. Thank you for watching.